All right, question 14. Long-term records from the Serengeti National Park in Tanzania show interesting ecological relationships. When wildebeest are more abundant, they graze the grass more heavily, so there are fewer fires and more trees grow. Lions feed more successfully when there are more trees, so the lion population increases. Researchers collected data on one part of this cycle, wildebeest abundance, measured in thousands of animals, and the percent of grass area burned in the same year. The result of a least squares regression on the data are shown here. All right, so we see that there is a downward trend, which makes sense because it says here, when wildebeest are more abundant, there are fewer fires. Okay, so we would expect a lower percent area burned when there's more wildebeest. Okay. All right, here's the residual plot, and then we have computer output, which would help us construct the equation. Okay, part A. Is a linear model appropriate for describing the relationship between wildebeest abundance and percent of grass area burned? Explain. Okay, so the appropriateness of the model can be determined by looking at the residual plot. Is there any leftover pattern here in the residuals? Okay. Now, I'm not seeing any clear smiley face or frowny face patterns. I'm not noticing any megaphone patterns where the points are kind of increasing or decreasing as you go left to right. To me, this looks really random, right? Which is a good thing, right? Because it means that the model that we fit here is describing the majority of the pattern, and so there's no leftover or residual pattern to see. All right. Now the R-squared value isn't super high, right? It's only 64%. And I think that's because the points aren't like super tightly close to the line. There's going to be a decent amount of space. But still, I think a linear model is more appropriate as compared to trying to transform the data. I don't think we would need to do that. Okay. So I'm going to say yes to this, and it's because the residual plot shows that there is no leftover pattern. Okay. In other words, the model is doing a good job of describing all of the existing pattern. All right, did not write that too well. Okay, part B, give the equation of the least squares regression line. Be sure to define any variables you use. Okay, so that just basically means don't just write y and x in your equation, but use context. All right, so here's our context. Wildebeest population is the x variable. Wildebeest is the x variable. Percent burned is the y variable. Okay, the slope and intercept are right here. Right, so that's our y-intercept, the one that's called constant, and then this is the slope, right? Remember, the slope multiplies the x variable, which in this case is the wildebeest variable. Okay, so we will say predicted percent burned equals 9229 minus 0.05762 times wildebeest in the thousands. Okay. If you're not familiar with the wildebeest, I would suggest go watch The Lion King. R.I.P. Mufasa. All right. So there's our equation, and it has the context, right? Our variables are there. Part C. Interpret the slope. Does the value of the y-intercept have meaning in this context? If so, interpret that. If not, explain why. Okay, so the slope measures the rise over the run, or as we prefer to say, the change in y versus the change in x. Okay, so the slope is negative 0.05762. As a ratio, it'd be over 1, right? So as X changes by 1, or in this case, as the wildebeest population increases by 1,000, the Y variable, the percent burn, is predicted to decrease by 0.05. Now, is that 0.05 or is that 5%? Well, these are written on the 0 to 100 scale. So that's a very small amount then. Yeah. Okay. Right. So let me try writing it this way. The predicted percent burned, I cannot write tonight, percent burned decreases by 0.05762% for every additional 1,000 wildebeest in the population. Right. In other words, adding 1,000 wildebeest to the population isn't going to do much to the percent area burn. It's only going to decrease it a tiny fraction. So you'd have to add, hundreds of thousands or maybe millions of wildebeest to get a meaningful decrease in the percent burned. Okay, the y-intercept now. So the y-intercept describes what's predicted to happen if there are no wildebeest in the population. So if there's no wildebeest in the population, the model would predict 92% of the area would be burned. Let's move our work to create more space. Okay. So if there are 0 wildebeest in the population, the predicted percent of area burned is 92.29%. Now, in both of these sentences, right, it's important that you say predicted, right? We're not talking about what actually happens, but what the model predicts is going to happen. Okay, now is it reasonable to think that there could be 0 wildebeest in the population? Probably not. I don't know, what's the lowest value here? Right, so there was a point in time when there was less than 100,000 wildebeest, but to say that there's 0 wildebeest, right, like that the species went extinct, I don't know. I guess it could happen, but realistically, I don't think it would happen anytime soon. So I don't know. I'm going to just go ahead and stick with that interpretation, right? If the wildebeest population were to go extinct and there were none, then this model would predict 92% area burned. All right, part D. Interpret the standard deviation of the residuals and R squared. Okay, so the standard deviation of the residuals is this value labeled S, and you can think of it as the average prediction error by the model, right? So when we make predictions with this model, they will tend to be off from the truth, in this case by about 15.9%. Okay, so predictions made with this model will typically be off or in error by about 15.988%. Now I should probably add a little bit of context there, so I should maybe say predictions for the percent of area burned using this model Yeah, that sounds better. Let's modify that. Okay, predictions for percent area burned using this model. All right, predictions for percent area burned using this model will typically be off by about 16%. Okay, r squared, right? That's the percent of variation in the y variable explained by the model. So we could say about 64.6% of the variation in percent of area burned is explained by the linear model with wildebeest population measured in the thousands. Okay. So knowing the size of the wildebeest population is helping to explain a reasonable amount of the variation, but not all of it, clearly, but a decent amount.